Okay, so good morning, everybody. We are going to continue the course on Malliavin calculus, okay, applied to the computation of Greeks in finance. And today we are going to start the technical part of the course, and I think that I will need 3 sessions, okay, in order to do this technical part. Okay, so keep in mind that according to what we have done in the previous session, my aim, okay, we have seen that my aim is to obtain integration by part formula that are related to the Ito integral, let's say, okay, in order to be able to compute the Greeks efficiently in finance, okay. And we have seen during the previous session that I have already an integral that is the Ito one, okay, and I need a derivative operator, okay, with some nice relation with respect to the Ito integral. And in fact, this derivative operator is the operator that we are going to define today, okay. So today I will define it, okay, and we are going to study some of its properties, okay. So I split my screen, okay, and we are here. Okay, so first of all, I want to remind, okay, at the beginning of these sessions, the notations, some of the notation I have previously introduced, okay? So remind that for this course, excuse me, so it's not the one we are going to use, just let me once again, okay? It's this one that I want to use, okay. So I have introduced the following notation. So the probability space we are going to work with, okay, is a particular one. I remind you that for me and in all this course, omega will be the set of the continuous mapping from 0 capital T into R such that f of 0 is equal to 0. For calligraphic A, the sigma algebra, I will take the Borel sigma algebra related to omega. Omega is a Barnard space when equipped with the infinite norm, the norm of the supremum. Okay, so the Borel sigma algebra here is just the sigma algebra generated by the open sets related to this norm. And for mu, I will take what I have called the Wiener measure. Okay, and the only thing that you have to keep in mind is that with this triple, okay, then I am able to define in a more concrete way as usual the Brownian motion in this way. So for this course, okay, I repeat that the Brownian motion BT will be a mapping from omega into R, and I can give an explicit form to this mapping. It associates to W, that is a continuous mapping from 0 capital T into R null at 0. I associate simply WT. In particular, according to the definition of omega, okay, B0 is equal to what? So B0 is the mapping that associates to W0, and I know that W0 is equal to 0. So I have a Brownian motion that starts at 0. And I know that under mu, this mapping is a Brownian motion. Okay, so it's the way to define the Brownian motion in this course. And you are going to see today, okay, that it will simplify a little some computations, okay, to consider the Brownian motion this way. Okay, so it's the first notation that I want to introduce, and I also remind some notation that I will use hereafter. Okay, so for me, L2 of omega will be the L2 space associated with the triple, so omega, F capital T, where F capital T is the filtration of the Brownian motion at time capital T, and mu is the Wiener measure, okay? So it will be L2. And I have a scalar product on this space, okay? That is just the expectation of the product of the random variable because they are in L2. I will also consider the space L2 of 0 capital T, that is in fact the L2 space associated with this triple, 0 capital T, the Borel sigma algebra related to 0 capital T, and here you have the Lebesgue measure on 0 capital T, and you have on this space a natural scalar product, okay, that I will denote by this bracket, okay, and I remind you that this scalar product is just equal to, okay, so Fj, if I have two elements in L2 of 0 capital T, here will just be the integral between 0 and capital T of f of s, g of s, ds. So we have here two Hilbert spaces, okay? So here I can remind you that if I have, okay, let's say u and v, the scalar product in L2 of omega here is just the expectation of the product. Okay, so you have here two Hilbert spaces, okay? I will also introduce this set of mapping from R to the power n into R, okay? F C infinity P R n R, what is this? So it's the set of the mapping of class C infinity here from R to the power n into R, okay? So that I have partial derivatives at any order, and these derivatives are continuous, okay? And I suppose, so it's for the P means polynomial growth, okay? So I want that F and its derivative have polynomial growth. So what is the meaning of this? I will say that H from R to the power n into R as polynomial growths if there exists, okay, let's write it Q from R to the power n into R, Q being a polynomial, such that the limit when the absolute value and the norm of x, in fact, goes to plus infinity, okay, the limit when the norm of x goes to plus infinity of the absolute value of h of x over q of x, okay, but I have something that is bounded, okay. So what is the meaning of this one? It means that if the norm of x is big enough, okay, h is less than a constant multiplied by a polynomial, meaning that in plus, when the norm goes to plus infinity, the behavior of the mapping H is controlled by a polynomial. So it means that I can go to plus infinity, but okay, at a speed that is controlled by a polynomial. Okay, so if you want, you can say that H of x is less than k q of x for x big enough in the sense of the norm. Okay, so I can control my mapping by a polynomial. So, and what I want for the mappings belonging to this set, I want them to be of class C infinity, and I want that the mapping and all derivatives or partial derivatives, okay, are controlled by polynomial this way. It means that I can control the behavior of f and of all its derivatives, okay, when the norm goes to plus infinity. Okay. So it's the sets, the functional sets we are going to work with, okay, to define the derivative operator. And in order to define the derivative operator, we are going to do more or less what we have done in the definition of the Ito integral. What I have done when I have defined in the first semester the Ito integral. First, I have defined it for elementary stochastic processes that are, okay, roughly speaking, stochastic processes that are piecewise constant, okay? and you have a formula for this, okay? And we have seen that with this formula, we obtain an isometry, and this isometry allows us to extend the stochastic integral to all the stochastic processes that are progressively measurable and square integrable, okay? So it's what you have done with Mr. De Meyer during the first semester. And here we are going to consider an analogous ID, not exactly the same, but an analogous ID, that is, we are going to propose a definition for the derivative operator for elementary random variables. And then we are going to see if it is possible to extend it for more general random variables. And the idea is to have a domain of definition for this operator that is big enough in order to contain, okay, a lot of random variables. Okay, so it's exactly what we are going to do now. First, we are going to define the derivative operator for elementary random variables. We are going to study some basic properties, and then we are going to see that these basic properties allow us to extend it to more general random variables. But first of all, okay, I need to specify what I mean by elementary random variable in this course. So it's what we are going to define now. Okay, so I will denote by calligraphic S the set of elementary random variable in this course. So I said that F belongs to calligraphic F if there exists an integer that is not zero, if there exists n element of L2 of 0 capital T, and a mapping F that belongs to the set of the mappings of class C infinity with polynomial growth, okay, such that, in fact, capital F is equal to F of the Wiener integrals that are related to this H1, H2, Hn belonging to L2 of 0 capital T. So if you want to simplify a little, I can say, roughly speaking, that for me, an elementary random variable will just be a regular mapping of Wiener integrals. Here inside, I have my Wiener integrals in such a way that by regular, I mean that this small f has to be of class C infinity with polynomial growths. Okay, so it's what I will call the set of elementary random variable in this course. Okay, so I will do a few definition. First of all, you know that the integral between 0 and capital T of hi of s dbs, okay, I have here a Wiener integral as defined in the stochastic calculus course in the first semester. And I know that this follows a centered Gaussian random variable with a variance that is equal to hi square s ds. Okay? So it means that any, okay, Wiener integral is Gaussian, so it has, okay, moments of all order. Okay, what is more, I have here, using the linearity of the Wiener integral, I have here a Gaussian vector. Okay, so it has a consequence of the moments on the moments of capital F, because what can I say about capital F? Okay, capital F is a random variable equal, so having this form here, and with F that is of class C infinity with polynomial growth. So according to what I have said previously, I can say that the absolute value of F is less than what? So it's the absolute value of this quantity, but I know that f is of class infinity with polynomial growths, and so that, okay, I have something that is less than, let's write it this way, q, or a constant, time q, that is the polynomial, okay, of my Wiener integrals. So here you have a polynomial, okay, depending on this Gaussian vector. But I know that, okay, if I consider, okay, products of element of a Gaussian vector, okay, but they have all moments of all order, okay? And so I can say that here, this one, okay, belongs to LP of omega for all P belongings to N or to N star, okay? And so this one fulfills, according to this inequality here, fulfills good integrability conditions in the sense that this random variable has moments of all order because it is a regular mapping, okay, with polynomial growth depending on the Gaussian vector. Okay, so it's the aim of the first remark, small a here. Okay, I have this. A second result that will be important for us is the following one. So it's something that we are going to suppose, okay? The fact that, so I have seen that S is included in the LP of omega for any P, okay? But in fact, we have more than this. We have not only an inclusion, we have also the fact that S is dense in LP for all P belongings to N star. Okay, so we have the density of F's in LP. So I know that S is included in LP, but in fact, okay, I have a lot of element in F, okay, and sufficiently, and S is sufficiently big in order to answer its density. And what is the meaning of the density? It means that, okay, I have the following. If F belongs to LP of omega, there exists a sequence Fn in S such that Fn converges toward F in LP of omega. Okay? So we are going to admit the density of S in LP of omega. But if you want to have some precision concerning the proof of this result, so it's maybe something that you have proved with Mr. De Meyer in the first semester, that is, okay, in fact, what is S? S is the set of regular mapping of Wiener integrals. And probably you have proved with Mr. De Meyer that exponential of Wiener integral is a set of random variables that is dense in, let's say, in L2 or in LP of omega. It's the same, let's say in L2. So exponential of Wiener integral are dense, okay, consider as a vector space. And in fact, what is a polynomial? What is an exponential? An exponential is just a polynomial, okay, with a degree that is infinite in some sense. So I can approximate in a good way an exponential by polynomials, explaining why, okay, S is dense in LP. So if you want to have more details, but it's not very important for the continuation of the course, but if you want to have an idea of the proof concerning this part, okay, you can see the chapter 3, the end of the chapter 3 of my stochastic calculus course. that is available on my website, the one that I do in IRFA. Because it's a result that is important in order to prove the martingale representation theorem or the Ito representation theorem, okay? You prove it for exponential of Wiener integral, and then you extend to general random variable using a density argument, and the density argument I use in the martingale representation theorem is the one I can use in order to prove the density of S in LP, or at the very least, the density of S in L2. But let's say that for this course, we are going to admit that this set of random variable is big enough, in particular, okay, it is included in LP and in fact dense in LP. That is, if I have an element in LP, it will be possible for me to approximate it by elements that are in LP of that are in S, excuse me. Okay. So this is my set of elementary random variables. And what we are going to do now, okay, is to propose a definition for what will be for us the derivative of such a random variable. Okay, we are going to provide a definition concerning the value of the derivative of this random variable, and then we are going to study the properties of this derivative operator. Okay, so it's what we are going to do now. Okay, so the derivative, so that we call the Malliavin derivative in general in the literature of an elementary random variable of the preceding form is, so keep in mind that it is a stochastic process. Okay, so the derivative will be a stochastic process. Okay, the time being on 0 capital T, it depends on so all W belongs to omega, defined this way. So I repeat that if you have f of this form, the Malliavin derivative of f at time t is given by this expression. So what is this expression? It's the sum of the partial derivative of f with respect to the ith variable at my Gaussian vector, okay, related to my Wiener integral here, multiply by what? Multiply by hi of t, that is what I have inside, okay, the Wiener integrals. Okay, so why not? Okay, and just remark that, okay, the derivative I've defined this way is a stochastic process. Okay, so the derivative will be a stochastic process. So let's see some example of such computations. Okay, so let's take the basic case where f is just a Wiener integral, simply. So if f is just a Wiener integral, it has the preceding form, okay, with n equal to 1 and f equal to the identity of R. Okay, so if I apply the formula, I have a single element in my sum because n is equal to 1. I have to consider the derivative of f with respect to the unique variable, and here it's the derivative of the identity that is equal to 1, okay, multiplied by h. Okay, so in this case, dt of f is equal to what? So let's say 1, that is the term coming from the derivative with respect to the variable, because the derivative of the identity is equal to 1, and multiply by h1 of t. Okay, so it's exactly what I have written here. That is a consequence of this formula. And typically, okay, we see that the derivative of a Wiener integral is the integrand, that is what I have inside the Wiener integral. And keep in mind that the derivative operator I want to define today, I want it to have some nice property with respect to the Ito integral. So here it's not nice property with respect to the Ito, but to the Wiener integral. That is a particular subcase of the Ito one. Okay, but okay, here I remark that the derivative of a Wiener integral is what I have inside. Okay, so I have, it's the starting point from a relation between the derivative operator I define this way and the Wiener integral. That is a particular case of the Ito one. Okay, so let's continue with the examples. So if I take here f equal, let's say, to Bs, with S belonging to 0 capital T. So here I have the Brownian motion at time S, okay? And what can I remark with this? I can remark that my Brownian motion is just something that I can write as a Wiener integral. This way. And so I can apply what I have done previously, that is dt of f is equal to what? By what I have inside, that is the indicator function of the interval 0s at time t. Okay? So dt of f, in the case where f is the Brownian motion at time s, okay, is simply the indicator function of the interval 0s. Okay? And in particular, I can remark that if t is strictly greater than s, then in this situation, t of f is equal to 0. Okay? So I have this. So let's copy this page. So I have this one for the Brownian motion. That is my second remark here. Okay, so let's erase what I have written here. You will have it on the previous slide. So dt of the Brownian motion at time s, okay, is equal to 0 if t is strictly greater than s, is exactly what I have written here. Third remark that is interesting. I say the following: if you have f that is an elementary random variable, so that is that has this form here, and if you suppose it to be fs measurable, I said that in this case, dt of f is also equal to 0 if t is strictly greater than s. So it's exactly the third remark I have written. So in some sense, okay, what you have here is a generalization of what I have proved for Bs in the previous part of the remark. Okay, so I have this. So let's see what I have this relation here. That is a direct consequence of what I have here. Okay, is a direct consequence of what I have here. So f is an elementary random variable. So it has its form here, and it is fs measurable. So if I consider the conditional expectation of f given fs, but since f is fs measurable, I know that I have simply capital F here, okay? And keep in mind that I have the right to consider the conditional expectation because I have here a random variable that has, okay, moments of all order. In particular, it is in L1 or in L2, Okay. So, and if I want to simplify a little this expression, I can write it this way. So it is f of the integral between 0 and capital T h1 of u dbu until integral between 0 and capital T hn of u dbu given FSB. Okay? So I have to express this conditional expectation. But as usual, okay, when you have a conditional expectation to compute or to simplify, okay, but it is often nice to distinguish, okay, a part that is FSB measurable, okay, FSB, okay, the Brownian filtration at time S, and a part that is independent. So keep in mind that for any I in one n, I can write this Wiener integral. I can decompose it using the Schall relation. So just to be coherent with my notation, I don't want to make confusion with the indexes, okay? So we are going to write u here, dbu. That is, so the integral between 0 and capital T may be seen as the integral between 0 and S plus the integral between S and capital T. And what it's nice is that this one is Fs measurable, and this one is independent with respect to Fs, okay? And it holds for all these Wiener integral here. And so, if I compute my conditional expectation here, my conditional expectation is what? I know from what I know from the course of probability that I can write this conditional expectation as a function of the measurable part where simply g of x1 xn is equal to the expectation of what? Of f of x1 plus the integral between 0 and capital T h1 of u dbu until xn plus the integral between 0 and capital T. Excuse me, it's not 0 here because it's the independent part. So I have here small s here and here. hn of u dbu. Okay, so it's this one that I duplicate for the n variables. Okay, so I have this conditional expectation that is given by this mapping of the Wiener integrals, but here my Wiener integrals are no more between 0 and capital T as in the initial definition of f, but are Wiener integral between 0 and s, okay? So let's duplicate this. I erase what I don't need, so I will keep it simply this part here. So what can I say? I know that f is very, very regular because f is of class infinity with polynomial growth. And by dominated convergence, I can prove that since f belongs to the mapping of class infinity with polynomial growth, but the same hold for J. It's just a consequence of the Lebesgue regularity theorems, because here, okay, keep in mind that I have something that is, okay, for it and all its partial derivatives at any order, something that is less than a polynomial, so I can apply without problem, okay, Lebesgue domination theorem, okay? So in order to summarize, I have defined f as J of these Wiener integrals between 0 and s, where this one belongs to C infinity P. And so I am in the situation where I can apply this formula to J depending on these Wiener integrals, okay? And from this one here, this one gives me that dt of f is equal to what? So I apply the formula for J. I have inside the Wiener integrals between 0 and s here. Okay, I have what I have here, that is here. Okay, multiply by what? But multiply by what I have inside the Wiener integrals. Okay, but keep in mind that here I am between 0 and s. Okay, so this Wiener integral is written as the integral between 0 and capital T of the indicator function of 0s multiplied by h1. So here I have indicator function of 0s t hi of t. And of course, from this formulation here, I see that if t is strictly greater than s, all these indicator functions are equal to 0. And so dt of f is equal to 0. So I have proved the third point here that tell me if I have something that is fs measurable, if I consider the Malliavin derivative at time t for t strictly greater than s, then this derivative is equal to 0. It implies that intuitively you can think the Malliavin derivative, okay, for this elementary random variable as a kind of derivation with respect to the Brownian trajectory, but if you compute dt of f, it's the derivation with respect to the Brownian trajectory until time t, okay? So if you have something that is fs measurable, and that is an elementary random variable in the previous sense, in the sense of the definition 1, then dt of f is equal to 0 for t strictly greater than s, okay? So it's a result that I have proved here for elementary random variables, okay? And we are going to see hereafter that it is a result that is true, okay, in more generality than for only elementary random variable. But I have this in mind, okay? So the derivative of a Wiener integral is what I have inside. In particular, the derivative of a particular time is equal to an indicator function. And then I have proved that if I am an elementary random variable that is fs measurable, dt of f is equal to 0 for t strictly greater than s. Okay, I have this. So let's have a look on the last remark here. So the last remark, that is this one. Okay, so what is dt of f? dt of f, I copy the definition. Of my, let's write it this way, of my Gaussian vector. Multiply by hi of t. So this is the stochastic process because I can add the variable w here, and you have w here and w here, okay? So you have here a stochastic process depending on t and w, okay? So what can I say concerning the integrability of this process? First, I see that here I have something here. So my partial derivative has polynomial growths. I have inside here a Gaussian vector, and according to what I have said previously, in particular, I am in all the LP spaces, and so I am in the space L2 of omega. So this one is in the space L2 of omega. Okay, so I have this. For this part, by definition of an elementary random variable, I know that the hi belongs to L2 of 0 capital T. Okay, so you have here a random variable. Here you have a mapping. This one is in L2 of omega. This one is in L2 of 0 capital T. And in particular, I can say that the product here, because this one only depends on W and this one only depends on T, okay, the product belongs to what? But to L2 of the product space. This one being vector space, if I do the sum, all this term belongs to L2 of omega times 0 capital T. Okay? So I remind you that, okay, the norm that I have on this space, okay, it's the classical one you have used in the first semester. That is, okay, the norm is equal to the square root of the expectation of the integral of the square of the process. Okay, so it's exactly what I have written here. dt of f is square integrable with respect to the two variables. A remark that is important is that even if I have a process that is square integrable, in general, it is not adapted to the Brownian filtration. In general, it is not adapted to the Brownian filtration. So let's see an example in order to prove this. If I take f equal to bs square, okay? So I can write what, okay? So if I want to compute dt of f, if I want to compute dt of f, I have to apply this formula. And I just remark that, okay, what is f? F is equal to f of the integral between 0 and capital T of the indicator function of 0s u dbu. This one is just bs, where f of x here is equal to x squared. I have the square of the Brownian motion here. So I can apply my formula with n equal to 1, okay? And what I obtain for dt of f, I have a single term in my sum. So I have here the derivative of f, that is 2 times identity that I have to apply to this Wiener integral. So I have 2 times bs multiplied by the h here. And what is the h? It's what I have inside the Wiener integral between 0 and capital T. That is what I have here. That is an indicator function. Okay. In particular, I see that if t is strictly greater than, strictly less than s, what is dt of f? Dt of f is equal to 2 times bs. And so I see that dt of f is equal to 2 times the Brownian motion at the greatest time, let's say. So I have something. So dt of f is not adapted to ft, because you see that here dt of f is fs measurable and not ft measurable. So be careful, because the derivative in the Malliavin scenes, okay, is a square integrable stochastic process in the sense of what you have seen in the first semester, but I have something that is not adapted to mild filtration, and in particular, not something that is progressively measurable. Okay, it's not something that is progressively measurable. Okay, so I have this. So a natural question may be, okay, this definition is quite unusual, so why we take it? So the first answer I can say is that I take it because, okay, it copes with what I want a priori for the Wiener integral. That is the first element of my remark. The derivative of the Wiener integral is just equal to what I have inside the integral. Okay, it's kind of relation that I want between the derivative I want to define and the Wiener integral here, or the Ito in the future. Okay, but keep in mind that during the previous session, I have also reminded that, so I will write it this way. F is a mapping from, so if f is an elementary random variable here, f is a mapping from omega into R, where omega is a Banach space. It is a complete, okay, normed space. Okay, and I have reminded to you that there exist classical definitions concerning the differentiation in this framework. We have seen together, and I have reminded to you that I have the notion of Fréchet derivative, that is in fact the extension of what we call differentiability in R to the power n. And you have also directional derivatives, okay? That is the analogous of what we can consider as partial derivatives in the usual case of R to the power n, okay? And a natural question, so we have seen together that the notion of Fréchet differentiability is something that is too strong in order to be adapted to my framework, because we have seen, keep in mind in particular, that a Wiener integral is not differentiable in the Fréchet sense in general. I need regularity on the integrand to have the Fréchet differentiability, but in general, it's not the case. Here, I only suppose that the HI are in L2, so there are no reason that I have more regularity on the HI than only the integrability condition. Okay, so Fréchet differentiability is not a good idea, but it remains the second idea of differentiation, that is the notion of directional derivative. And in fact, what I want to see in the last part of my remark too is that, in fact, this definition here is not very far, and in fact is very close to a notion of directional derivative, but in a particular direction, okay? So first, let's define what will be the set of the directions. I define here H1, that is what we call in functional analysis the Cameron-Martin space. So probably few of you have heard about the theory of distributions, but if you have, okay, just let me remind that the H1 space is just the set of the mappings in L2, okay, that are differentiable in the sense of the distribution with a derivative that is in L2. To be more precise, what is H1 is the set of the element H in L2 that may be written as the partial integral of an element in L2. Okay, H has this very, very particular form. Let's keep in mind that if H, oh, excuse me, if H belongs to H1, then H belongs to omega. Why? Because H0 is equal to what? But if I plug inside here, H0 is equal to 0. Okay. And what is T gives HT? It is the partial integral between 0 and T of G of S ds. Okay. And what can I say about this one? Of course, I have something that is continuous because it's the integral depending on the upper bound of an element in L2. And let's just me remind that how to prove the continuity of this mapping here, just to say that if I consider, okay, let's write it this way. The integral between 0 and T of G of S ds minus the integral between 0 and T prime of G of S ds, okay, by the Cauchy-Schwarz inequality, okay, by the Cauchy-Schwarz inequality, I can write it as, okay, something that is less than the square root of the absolute value of T minus T prime multiplied by, okay, the square root of the integral between 0 and capital T ds square ds. And here it's the Cauchy-Schwarz inequality that allow me, and you see that here, okay, I am in fact more than continuous. I am uniformly continuous because I have this inequality. When T goes to T prime, this term goes to 0, and so this one. So I have the continuity, and in fact more than continuity because the continuity is controlled by the difference between T and T prime. So I have something that is uniformly continuous. So if I am in H1, H1 is a subspace of omega. H1 is a subspace of omega. So what I want to do now, okay, remarking that H1 is a subspace of omega, is to make the link between the definition I have given to you and the notion of directional derivative for f in the direction of the elements in H1, okay? So if I suppose that I have W belongings to omega, and if I have, okay, H belongings to H1, okay, I can say that according to my previous remark that if I consider T gives WT plus epsilon HT, okay, excuse me, epsilon being a small real number, I have something here that belongs to, okay, omega. I have something that belongs of omega. It's a mapping that is continuous because W is and h is according to my little remark here. Okay, and keep in mind that I will take for h of t is equal to the integral between h and t of g of s ds. Okay, so I have something in omega. So keep in mind that bt of this mapping, w plus epsilon h, okay, but is equal by definition of bt. I keep in mind that the bt I have defined in this course is just this thing associated to any element in omega, its value at time t. Then bt of this one is simply wt plus epsilon h t. So if I write d of bt w plus epsilon h, okay, that is the Ito differential here. I obtain d of wt, that is in fact d of bt of w, plus epsilon d of h. But what is h? H is a mapping with bounded variation because it can be written this way. And I have here d of ht that is simply equal to gt dt. Okay? So why I write this way? I write this way because if I consider, okay, my f as an element of S, something like this. I can consider the following. I can consider f of w plus epsilon h minus f of w, okay, over epsilon. So if I consider this ratio and if I study the limit of this ratio when epsilon goes to 0, in fact, it means that I am looking for if f has a directional derivative in the direction of h, h being an element in h1, okay? F being an element in h1. So let's see what happened for this one. Okay, so maybe what to do, because I want to continue my computation. Okay, so I will just write the things this way. So here, f of w is given by this expression here. So no problem concerning this. Okay, f of w is given by, okay, this one. But what is this term here? We are going to use what I have written here. So f of w plus epsilon h, okay, is equal to what? I plug inside, it is f of the integral between 0 and capital T, h1 of s dbs of w plus epsilon h. And the same until, okay, the last. I just write the first component here because I don't have too much place here. But what is this one? This one has been computed here, okay? So I use this one here. And it means that I can write f of w plus epsilon h as f of what? So this integral is in fact here simply using this relation here, the integral between 0 and capital T, h1 of s dbs okay, of W, plus what? Epsilon, the integral between 0 and capital T, H1 of S, D of HS, that is this one, G of S, excuse me, ds, and the same for all the components. So if I want to be a little bit clearer, so I will have this one, I will duplicate one more, okay, this slide, in order to erase and to simplify a little the things. So if I summarize what I have done here, I am interested in this ratio. I can write it as, according to what I have written here, f of the integral between 0 and capital T, h1 of s dbs of w, plus epsilon, the integral between 0 and capital T, h1 of s g of s ds, and the same for the other. It's the term fw plus epsilon h minus the f of w, that is simply the term with the Wiener integrals. Over epsilon. And my aim is to study the limit of this one when epsilon goes to 0. But here, I have something that is just a mapping from R into R. Okay, I know that f inside is differentiable. Okay, I have epsilon in the n component. So if I compute this limit, it's just the computation of a classical derivative of a mapping depending on n variables. So when epsilon goes to 0, using the differentiation of compound mappings, okay, I can prove that the limit when epsilon goes to 0 of this term is what? But it will be, if you want, the derivative of this mapping at epsilon equal to 0, keeping in fact that keeping in mind that I have the epsilon here. I have only written the epsilon for the first component, but I have also it for all the other components. So I just have to compute the derivative of a mapping depending on several components. And so I will obtain a sum from I equal to 1 to n of the derivative of small f with respect to xi, okay, at the point with the Wiener integral inside. What's happened for this one, the derivative of this one at what happened for this one for epsilon equal to 0, multiplied by the derivative of what I have inside at 0. And here I have simply a linear mapping in epsilon. So the derivative of this one in epsilon is just this term. And for the component, it will be the integral between 0 and capital T, hi of s, g of s, ds. Okay, so my directional derivative in the direction of h is given by this expression. But you see that this expression is not very far from what I have here. In fact, this expression, I can express it using the dt of f here. It's what? It's the scalar product between dt of f w and the j that I have here, okay, in L2 of 0 capital T. So the limit of this term here when epsilon goes to 0 is equal to this one. The limit of this one is the directional derivative of f in the direction of h. and I see that I can express this directional derivative using the dt of f I have defined here. So as a nice interpretation of this relation that I have imposed in the definition 2, but you can see it according to my relation here between the limits, that dt of f can be seen as the directional gradient of capital F in the direction of h, and it holds for all the h belonging to h1. Keep in mind that the fact that h belongs to h1 here is mandatory in order to be able to write this expression here, exactly what I have explained in the previous slide, okay? So I am able to compute the directional derivative of capital F in the direction of the element of h1, and the directional derivative I obtain involves okay, the Malliavin derivative as interpreted as a directional gradient. So it means that this definition that may seem to be coming from nowhere is in fact related to what we do in classical analysis. But here we only be interested in this course, okay, in directional derivatives in particular direction that will be the element of H1, okay? So it was to make the link between, okay, classical analysis and what we do here, and to prove that it's not something that is completely different, okay? So I have this interpretation of the derivative in the Malliavin sense, okay? So it's a little bit technical, and it will be a little bit technical for also the 2 next courses, okay? But after you will see that with all these tools, we will be able to obtain nice integration by parts in computation of this, okay? So let's continue. So we are going to study, okay? So I will duplicate these slides because we are going to do the proof of this, this lemma here. Okay, so we are going to see different lemmas, okay, and corollary, okay, related to the definition of the derivative operator, okay? So in a corner, I will just remind that when f has this form, I will remind the definition of the derivative operator to be clear. I have dt of f that is equal to the sum from I equal to 1 to n df over d of xi integral between 0 and 1 h1 of s dbs. hn of s dbs multiplied by hi of t. It's the definition 2. Okay, so I said that if f is an elementary random variable in the sense of this course, if j is an elementary random variable in the sense of this course, the product is an elementary random variable, and derivative of the product fulfill the classical formula that is d u v prime is equal to u v prime plus v prime u. Okay, that is exactly that the derivative of the product is equal to j multiplied by the derivative of f plus f multiplied by the derivative of j. Okay. So why I have this? But here it's very simple to have this. And in fact, you are going to see that in general, the properties that we are going to prove in this course will be properties that we are going to prove in several steps. The first steps will be for elementary random variables or elementary stochastic processes. And in this case, the proof that we are going to do, you will see that in fact, the proofs, okay, are based on classical arguments of classical analysis. And then all the objective will be to try to extend them, okay, to more general situations. Here, what happened? I have F and J that belongs to S. Okay, so I have two mappings of this form here. Let's see. So let's write the things. I can write F as the integral between 0 and capital T H1 of S dBs and so on. And J, that is what? J of maybe other mappings. Okay, so I can write in this way. So integral between 0 and capital T. Let's write them, okay, to show you Hn of S dBs. And here I have H1 tilde of S dBs. And so I don't necessarily depend on the same number of Wiener integral. Okay, so I will put a P here. Okay, so I have this one. So a priori, N and P are not equal. Okay. But what is nice is that, okay, so I have these mappings, okay, and I said I can always consider that I depend on the same Wiener integral. I can always consider that I depend on the same Wiener integral. Okay, so let's write it the following. So if I defined, suppose that I defined, okay, F tilde this way, F tilde of x1, xn, xn plus 1, xn plus p, that is defined as f of x1, xn. I have the right to do this, okay? I just add variables, okay? And I can say that f in this situation is what? Is just f tilde of the integral between 0 and capital T, okay, of what? H1 of S dBs, integral between 0 and capital T, Hn of S dBs. And I can add these Wiener integrals, even if I know that according to this formula, they won't be involved in the expression, but whatever, I can add them. And so on. It will be HP tilde S dBs. Okay, so it means that I can express capital F this way, where F tilde, okay, depend on all the variables, all the Wiener integrals that are involved in these two decompositions here. I can do exactly the same for J, doing exactly the same argument with exactly the same thing, okay, defining G tilde of, so J tilde of what? I will write it this way. So J tilde of x1, xn, xn plus 1, xn plus p as J of what xn plus 1 xn plus p. So why I do this? Because in this way, I can write f times j as f tilde j tilde of all my Wiener integrals. So what I have here. Okay, all this one. So I see that f times j can be written as f tilde times j tilde of these Wiener integrals, where f tilde and j tilde, I have f tilde that belongs to S, j tilde that belongs to S, and so, excuse me, f tilde is of class C infinity with polynomial growths. J tilde is of class C infinity with polynomial growths, implying that f tilde multiplied by j tilde belongs to C infinity P. Okay, so I have this. Okay, so it implies that fj belongs to S because I have written it as a mapping here that is the product between f tilde and j tilde of what? Of that belongs to the class C infinity P. Okay, so regular mapping of the Wiener integral. So the product is in S. Now, if I want to compute dt of the product, now it's simple because I just have to use the definition. The definition applies to this product here. So where I am here. So let's write the things this way. Okay. So I have this. Okay. I have this. And from the definition 2, in order to compute dt of f times g, I use the formula that it's the sum of the partial derivative, okay, of the Wiener integrals multiplied by what I have inside the Wiener integrals. So let's write it. Okay, I will add a new page here. Let's write it this way. So I have what? I have that dt of fj is equal to what? So it's the sum from I equal to 1 to here n plus p d over d of xi of what? F tilde multiplied by j tilde of all these Wiener integrals here, integral between 0 and capital T h1 of s dbs, integral between 0 and capital T hn of s dbs, integral between 0 and capital T h1 tilde s dbs until integral between 0 and capital T hp tilde of s dbs, multiply by what? By multiply by what I have, okay, inside the Wiener integral in the ith position here. Okay, so I can write it this way. I can write it this way. So multiply, I will continue my expression here, multiply by what? So it will be two situations. It will be multiplied by h I of t if t or if I is between 1 and n, and it will be h I tilde E if I is between n plus 1 and n plus p. Okay, so I just use the definition 2 to write the things this way. I have a regular mapping of the Wiener integral. What is the definition of the derivative? The sum of the partial derivative multiplied by what I have inside the Wiener integral. But what is this? From classical analysis, I know that the partial derivative of a product fulfill the following formula. D f tilde over d of xi multiplied by j tilde plus dj tilde over xi multiplied by f tilde. So it's the classical formula for the derivative or the partial derivative of a product. So here it comes from, let's say, classical analysis. I have this, okay? Okay, so what I obtain, so keep in mind that what I have for I between 1 and n, okay? For I between 1 and n, so keep in mind on the definition I have given to f tilde and j tilde. So f tilde, in fact, depend on the first n variables, not the other one, and j tilde depend on the p last variables, okay, not the first. So for I between 1 and n, I have the following. D over d of xi of f tilde j tilde is equal to what? Here, it's simply d of f over d of xi multiplied by j tilde plus here 0 multiplied by f tilde. So I have simply this term. And for I between n plus 1 and n plus p, d over dxi f tilde j tilde is equal to what? It's equal to this term that is 0 because f tilde in fact doesn't depend on the last p variables plus dj over dxi multiplied by f tilde. So I have simply this term. And at the end, if you compute dt of fj using this formula and the fact that I have this property for the partial derivative that I have inside here, what I obtain simply that dt of f times g is equal to what? So for I have the sum here, okay, so I will write it this way. I can cut the sum in two parts, the sum from I equal to 1 to n plus the sum from I equal to n plus 1 to n plus p. The term that I will obtain here, if I plug inside and using that from I between 1 and n, I have only this term here. I will obtain j, oh, excuse me, I will obtain here capital J multiplied by dt of f. And here, keeping in mind that for I between n plus 1 and n plus p, I have only partial derivative with respect to j. I will obtain for this one here, okay, I will obtain for this one simply f multiplied by dt of j. And so I have the classical formula for the derivative of a product, okay, that is dt of fj is equal to g dtf plus f dtj. Okay, so to summarize, the lemma 1. Okay, so it seems to be a little bit complex, but in fact, I just have to handle notations here. I handle notation, and you see that the only real argument that I use, okay, is this one. The real argument I use is the derivative, okay, the partial derivative of a product using the classical formula. It's what I obtain, okay, what I use in order to obtain my formula. And using this basic argument, and then just after handling notation, I obtain from the formula concerning the partial derivative of a product in the classical sense, I obtain the lemma 1 that tell me that if I have two elementary random variables, the product is an elementary random variable, and that the derivative of the product fulfills the classical formula. And here it's something that is important, because keep in mind that it's what I have reminded in the previous session, that what is an integration by part formula? An integration by part is a derivative operator, an integral, and by the integration by part formula, that is a consequence of the formula of the type uv prime is equal to u prime v plus uv prime. And here you see that the derivative operator that we have built together, okay, fulfills a classical product rule principle. Okay, that is the derivative of a product fulfills the good formula, u prime v plus uv prime. Okay. Okay, so I have this. Maybe we'll do a little break. So see you in 5 minutes. Okay, so let's continue what we have started. Okay. So I have proved the lemma 1, okay, that for elementary random variable, product is an elementary random variable, and that the derivative of the product fulfill the classical formula. So now we are going to prove the lemma 2 and the corollary 1, that are something that we can call, okay, a first step toward an integration by part formula. Okay. So we are going to prove the lemma 2, but before, okay, let's have a look on the corollary if I admit for the moment the lemma 2. Okay, so it works with my pen. Okay, so I have proved the lemma 1. I admit for the moment the lemma 2, and let's see that the corollary will be a basic consequence of lemma 1 and lemma 2. Okay, so in fact, what we are going to do, so I take f and j in S. I know from lemma 1 that the product belongs to S. So if the product belongs to S, I can apply the lemma 2. My lemma 2, what can I say? I can say that I have this relation here, and this relation is already a kind of integration by part, because you see that here you have a derivative on F, derivative on F that disappear in this expression here, and here you have H, and it makes appear an integral. So making disappearing the differential here, the derivative, you make appear an integral, okay, with respect to the Brownian motion. Okay, so if I apply the lemma 2 that I will admit for the moment, so I apply it for the element f times j that is in S. I have expectation of the scalar product between d of fj and h in L2 of 0 capital T that is equal, according to this formula, to the expectation by lemma 2 for fj belonging to S, multiplied by the integral between 0 and t, h of S dbs. But by the lemma 1, I know that the derivative of the product fulfills this relation. So I have here the expectation of what? Of g df plus f dj h L of 0 capital T. So you have the product in L2 of 0 capital T of this one. Okay, so I have the scalar product, so I can use its bilinearity. So I can separate this in two terms. That is the expectation of scalar product G df H plus expectation of f dj H. And what happened for this one? Here you have a J that is a random variable, not a stochastic process. That is, it is independent of T. Here, scalar product with respect to the time. So this one, I can in fact remove the G from the scalar product because it doesn't depend on the time. And the same all for the other term because F doesn't depend on time. So I obtain this one. And if I summarize what I have obtained, I have that this term here is equal to the sum of these two. And so I obtain simply this relation, okay, passing this one to the other side of the equality, okay? So the corollary one is just a basic association of the lemma 1 and the lemma 2 applied to the product of two elementary random variables, okay? So it's okay for the proof of the corollary one. And here you see that you have a kind of integration by part formula with the three classical terms, okay? You have here j, the derivative of f, here f, the derivative of j, and here the derivative disappear, making appear something that is the integral of h with respect to the Brownian motion. Okay. So I have this one. Okay, so it closes the proof of the corollary one if I admit the lemma 2. So let's do the proof of the lemma 2. So once again, you are going to see that up to notations or up to simplifications, this lemma 2, that is a way to make disappear the derivative here, making appear an integral here, will be based on an argument that is just a classical integration by part formula in the classical framework you usually know, that is, okay, with respect to the Riemann integral and the classical derivative. Okay, so proof. So in order to make the proof of the lemma 2 easy, okay, so let's keep in mind that my f here is an elementary random variable, so it's something of this form here. I have this one, and I have an h belonging to L2 of 0 capital T, meaning that I have in fact n plus 1 element of L2 of 0 capital T that are h1, h2, hn, and the h here. So I say the following. I can always suppose that h is equal to H1 and that H1 Hn is an orthonormal family of L2 of 0 capital T. And what is the meaning of being an orthonormal family? Okay, it means that I have here mappings with norm 1, that is, okay, the norm of Hi in L2 of 0 capital T is equal to 1. Okay, it's the meaning of being normal. Okay, the norm is 1 for all of them. And if I consider the scalar product in L2 of 0 capital T of two different mappings, okay, I obtain 0. So they are orthogonal with norm 1. It's the meaning of orthonormal. So the question is, okay, why it is always possible to do this? So I won't write the things in all the details, okay, because it is a little bit boring, but I just want to show you the intuitions concerning the fact that I can always suppose that I have this. Okay, so maybe I will add a white page here. So I start from H, H1, and Hn, okay? So concerning H1, Hn, okay, you have, okay, in, it's a classical tool of linear algebra, a way, or in fact of Hilbert space theory, okay, you have a way to transform, okay, this family. So there exists E1, En, that is orthonormal, such that the vector space generated by H1, Hn is equal to the vector space generated by E1, En. So this result here is what we call the Schmidt orthonormalization process. What is the idea? So I have a family that is an arbitrary family of vector in L2 of 0 capital T, and I want to transform it into an orthonormal family, that is a family where all the vectors have norm 1 and they are orthogonal together, okay? And with the two generated vector space that are the same. So let me remind you in a few seconds, okay, what is the principle of this orthonormalization process? So I start from H1. I want to make it with a norm equal to 1. So I can write, I transform it into E1, that is H1 divided by its norm. Okay, in this way, I have the norm of E1 that is equal to 1 by construction. For H2, I want to make it with norm 1, okay, and orthogonal to the previous one. Okay, so what can I do? I can transform H2 into H2 minus the scalar product between H2 and H1, okay, this way, okay. So if I do this, what I obtain? I obtain a vector, okay, such that now, so I have H2, H1 that is 0. So the vectors are orthogonal. And if I want to make it, okay, with norm 1, I just divide by the norm of H2 minus H2, H1, H1. And so this way I obtain E2, if you want, this way, that fulfills, okay, what? That fulfills E1, E2, 0. The norm of E1 by construction is 1, and the norm of E2 by construction is equal to 1. Also. And so on. I take the third, I subtract, okay, but the things corresponding to the projection on the two first vectors. I divide by the norm, and I will obtain a third vector that is orthogonal from the two previous one with a norm equal to 1, okay? And you see that all the transform I use here are linear transform. Linear transform explaining that the vector space that is generated by H1, Hn will be exactly the vector space generated by E1, En, because in order to transform H1, Hn into E1, E2, En, I just use linear transformation. Okay, so by the Schmidt orthonormalization process, it's easy to transform an arbitrary family into an orthonormal one having this property. Okay? So I have this. Concerning the first vector H here. So for H, here, I have an orthonormal family. So I have, if you want, the beginning of a basis in L2 of 0 capital T. So H may be written as the sum from I equal to 1 to N of, I use the decomposition on this, okay, orthonormal family. So I have HI, HEI plus an extra term here that will be an extra term that is orthogonal to the vector E1, En. So it will be orthogonal to the vector space generated by these vectors because, okay, I can complete this family into a basis of L2 of 0 capital T, okay, into a basis that is an orthonormal basis. And in fact, if you do this, okay, you see that I can transform my initial family into a family that is an orthonormal one with each vector maybe explaining as a linear combination of the first, okay? And for H, okay, I can write it as linear combination of these vectors here plus a term that is orthogonal. And in fact, if you do this, okay, and if you go back to this expression here, you see that if you linearly modify H in this expression, you have linearity of this expression in H, linearity of this expression in H, okay? And you have a relation that is compatible with orthogonality arguments. So I can always come back to this situation. Okay, I can always come back to this situation. That is a situation where the H1, Hn in H are not arbitrary, but the situation where H is in fact the first element of this family this family being supposed to be orthonormal. Okay, so I won't write the things in all detail, but this is the principle. Okay, because here you have something that is deeply related to linearity and to orthogonality. Okay, so let's suppose now that I have this. Okay, let's suppose that I have this. So I continue here. So now I am in the proof of the lemma 2. With the hypothesis that H1, Hn orthonormal family of L2 0 capital T, and such that H is equal to H1. And I want to do the proof. So if I do the proof, I can remark that since I have an orthonormal family here, I have here n Wiener integrals, okay, corresponding to elements in L2 that are orthogonal with norm 1. So you have here I, ID, N01. So the density of the vector of my n Wiener integrals is just phi of x, that is the product of the density of each component, that is, okay, 1 over the square root of 2 pi to the power n exponential minus the sum from I equal to 1 to n of xi squared. So the density of this vector is given by this expression, okay, the classical expression for the density of n independent n01. It's the product of the density of, excuse me, here it's over 2 here, huh? The quotient density. Okay, so now if I want to express now this quantity, what is this? This quantity is equal, so I apply the definition of d of f, for f being equal, excuse me, to this one, okay, regular mapping of these Wiener integrals here. So it's expectation of what? Of sum from I equal to 1 to n, df over dxi. I use the definition, definition 2. I have inside the Wiener integrals. I multiply by hi, and I have a scalar product with h. Okay? Here, I have something that is independent. Here, the partial derivative depends on this Wiener integral, so it is independent of the time t. Okay, so I can write this thing as the sum from I equal to 1 to n of the expectation of df over dxi, okay, applied at this Gaussian vector. And I have the scalar product between hi and h, okay? But from my hypothesis, I know that h is equal to h1 and that the hi are an orthonormal family. So it means that this term is equal to 0 if I is different from 1, and this term is equal to 1 if I is equal to 1. So I have here simply the expectation of df over d of x1 binary integrals inside, multiply by 1. Okay, and it's here that my little transform at the beginning allow me to simplify considerably, okay, but the value of these scalar products, because, okay, if I don't do this, it's possible to do the proof directly, but you will have to handle this scalar product. And in my little transform at the beginning, I allow me to work with scalar products that are every time 0 except for I equal to 1. Okay, so I repeat that I have the expectation here of d of f h that is just equal to the expectation of d of f over d of x1. I write inside my Wiener integrals. But this expectation, since here I have n independent and 0, 1, I can write this as an integral with respect to r to the power n of f, the partial derivative of f with respect to the first variable at the variable x1, xn, multiplied by the density of this Gaussian vector. And I know that the density of this Gaussian vector is, okay, what I have denoted by phi of x, that is just the product of the density of each random variable. And I remind you that this one is given by 1 over the square root of 2 pi to the power n over 2 sum exponential of minus 1 over 2, the sum of the xi square. Okay, I remark in particular that d of phi of x with respect to the first variable can just be written as minus x1 phi of x. Simply, I compute the derivative with respect to the first variable. Here it's assumed from 1 to n. And now we are going to do, okay, an integration by part with respect to the first variable here. Okay, integration by part with respect to the first variable. So if you want to be correct, I use Fubini theorem in order to write this integral as an integral with respect to the n-1 last variable and an integral with respect to the first variable. And considering the integral with respect to the first variable, I do an integration by parts. So here I use Fubini plus integration by part classical one in the variable x1. And I obtain what? So I obtain, if I do the job, okay, I obtain the integral with respect to r to the power n of f of x1 xn phi of x dx minus the integral of what? So f of x1 xn, the derivative of this one, the derivative of this one being equal to minus x1 phi of x. So I have a double minus, so I have a plus, okay, what? The integral with respect to r to the power n f of x1 xn x1 phi of x dx. And that we have this. Okay, but now it's finished because what is this? Excuse me, it's not what I need to do here. Okay, so it's in fact, so it's not what I have here. It's not what I have. It's not correct to write this way, excuse me. If I want to write it properly, I will write it this way. for x1 equal to plus infinity, x1 equal to minus infinity, and I have here d of x2, d of xn. Okay, I use the classical integration by part formula, but here, what I remark, here I have a mapping with polynomial growth. Okay, here I have phi that is a negative exponential. So if I compute the limit in the variable x1 and in the variable x1 going to plus infinity, so when x1 goes to plus infinity, the other variable being fixed, this one goes to 0. The same hold when x1 goes to minus infinity because I have a square here. So this term is equal to 0. And finally, I have simply the integral r to the power n, f of x1, xn, x1, phi of x dx. And here I pass from an expectation to an integral. Here I can do exactly the converse, keeping in mind that phi of x is the density of this Gaussian vector. And so I can express the things here this way: expectation of f of my vector of Wiener integral multiply by what? Multiply by x1 here. And what is x1? x1 is just the first element of my random vector, that is the integral between 0 and capital T of h1 of s dbs, with h1 that is supposed to be equal to h. So I have this one. And at the end, what I obtain the expectation of what? So f of these Wiener integrals is equal to capital F multiplied by the integral between 0 and capital T of h of s dbs. This equality here being exactly the result I want to obtain here. And what is nice to remark is that up to my argument that tell me, okay, I can simplify a little bit the things at the beginning, supposing that I have between the mappings in L2 of 0 capital T some orthogonality constraints, okay, and the fact that the vector h can be considered as h1. In fact, here you see that the only real argument that I use in order to prove this formula is just here, the integration by part formula that I use here with respect to the Gaussian density function. And that's why I am able to transfer the derivative here into an integral with respect to the Brownian motion here. And if you have in mind what I have done in the second course, okay, where I have obtained, okay, some weight for the computation of Greeks in the Black-Scholes model, it's exactly what I have done. The Greeks were obtained in the Black-Scholes model doing integration by part with respect to the density of a Gaussian distribution. And here, in fact, it's exactly what I do. Okay? So I have proved these two lemmas and the corollary, telling me that for elementary random variables, the derivative of a product may be computed using the classical formula. That I have this kind of duality between the derivative and the Wiener integral for elementary random variable. That is, the expectation of the scalar product between the derivative and h is none other than the expectation between f and the Wiener integral with an integrand that is h. And applying these two results, I did use something that looks like, okay, a classical integration by part formula, where here you have the project fg, here g f prime, let's say, and f j prime, okay? So it's a first step concerning, okay, integration by part formula that I want to obtain in this course. So for the moment, what I have seen, I have defined the set of elementary random variables. I have defined the derivative operator for this elementary random variable, proving that this operator, in fact, is a kind of directional derivative in the direction of the Hermann-Martin space. I have proved that for elementary random variable, this derivative operator fulfills the classical product rule principle. Okay, that is uv prime is equal to u prime v plus uv prime, the lemma 1. And then, okay, the lemma 2, that is a kind of duality or integration by part, okay, between the derivative operator of an elementary random variable and the Wiener integral. Okay, so we have this. So it will be enough for the derivative operator for elementary random variable. Now the question we are going to answer is it possible to extend in a good way the definition of the derivative operator for more general random variables? Okay, so it's the question I want to solve in the next slide. Okay, what we are going to do. So the principle is not very different from what the technique you have used, okay, in the construction of the Ito integral, where once you have defined the Ito integral for elementary stochastic processes that are progressively measurable and square integrable, using the Ito isometry, you have extended the result to whole L2 prog. Here, okay, we won't have a kind of isometry property, but we are going to have, okay, this. That is not an isometry property, but in some sense, we have this, okay, that the scalar product between these two, okay, in L2 of omega is equal to the scalar product between df and h, okay, in L2 of omega times 0 capital T. So we have a kind of transform that preserve, okay, the scalar product. Okay, so what is the main idea, okay, in order to do this? So I am in the situation where what I have done, I have defined D, so the derivative operator in the Malliavin sense, on the elementary random variable. But I have said at the beginning of the session that the elementary random variable are dense in L2 of omega, okay? And the idea we want to use is to extend D using approximating sequences, okay? So if I have an element F that is in L2, using the density argument, I know that there exists a sequence of elementary random variables that are element in S, such that Fn converges toward F in L2 of omega. This is the density point here, and such that the derivative in the Malliavin sense is well-defined because what I have done in the definition too. Okay, so what may be a natural ID? Fn converges toward F, dt of Fn is well-defined. In some sense, I want, if it's possible, to define the derivative of F, and how to do? But to define it as the limit of dt of Fn, okay? It's something that is quite natural. Fn converges toward F, dt of Fn is well-defined. What may be a natural ID in order to define dt of F is to consider the limit of these terms. The problem is that the limit doesn't exist necessarily. We are not in the situation of the integral. In the Ito integral, okay, you know that you have an isometry. So if you have something that converges at the beginning, by the transformation, it will be convergent because I have an isometry. Here, I don't have such an isometry property. So I said the following. An ID to define D of F is to say the following. I have this situation. I have an approximating sequence where the dt of Fn are well defined. If this sequence is convergent in L2 of omega times 0 capital T, keep in mind that you have a stochastic sequence of stochastic processes here, okay? If it converges, it should be natural to define D of F this way as the limit, so the limit in L2 of omega times 0 capital T of this derivative. But you see that you have a condition. If the limit exists, then it is natural to define d of f as the limit of the derivative of my approximating sequence. And it's the idea we are going to explore in the next slide. But at this stage, okay, why I have a problem if I want to do this? I have a problem if I want to do this because but here I said that, okay, if I have an element in L2, there exists an approximating sequence, and I can define the derivative this way, why not? But nothing tells me that what I have defined here is independent of the choice of my approximating sequence. I have to prove that if I want to do this, if I change Fn into another approximating sequence, the limit here is the same. Okay, so it's what I have to prove if I want to prove that I can extend my derivative operator using this ID here. Okay, so using approximating sequences such that the limit of the derivative exists, and defining this way the derivative of my limit as the limit of the derivatives. Okay, so the first problem I have to solve is to prove that I am independent on the choice of my approximating sequence. And it's exactly what we are going to do now. The result we are going to prove this way is this one. It's this proposition that will allow me to define the derivative using the previous ID in a way that is unambiguous. So what is the meaning of this one? And why? So I just duplicate in order to do the proof after, okay? So this proposition tells me the following. I said that if Hn is a sequence in S such that Hn converges towards 0 in L2 of omega, and such that the family of stochastic processes D of Hn converges towards C in L2 of omega times 0 capital T, and where C is a stochastic process, it depends on time and on W, then necessarily C is equal to L2 of omega times 0 capital T. If you have followed the course of functional analysis in the first semester, this property is called the closability property of the operator D. When Hn goes to 0, and if D of Hn converges toward C, C is necessarily equal to 0. Okay, keep in mind that it's not the continuity property at 0 here, because continuity property at 0 would say that if Hn goes to 0, D of Hn goes to D of 0, that is equal to 0. It's not what I have here. It is if Hn goes to 0 and if D of Hn is convergent, then okay, the limit is equal to 0. I need to impose, okay, the fact that D of Hn is convergent, something that you don't have to impose when you study the continuity at 0 of the mapping. Okay, so before to do the proof of this proposition 1, let's see that in fact this proposition, okay, allow to overcome the previous ambiguity in the definition of, or in the extension of the derivative operator. So keep in mind that I want to prove that I have here something that is independent of the choice of an approximating sequence. Okay, so suppose that you are in the following situation. So you have f that belongs to L2 of omega. So I suppose that I have a sequence Fn in S such that Fn is an approximating sequence. Okay, I have the right to consider this, okay, because of the density of S in L2 of omega. And I suppose that D of Fn is convergent in L2 of omega times 0 capital T. And suppose that I have it for one approximating sequence, but I have also it for another one. So suppose that you have another sequence, Gn, in S, such that Gn approximate F in L2 of omega, and such that D of Gn is convergent in L2 of omega times 0 capital. In fact, I can use this proposition. If I define Hn as Fn minus Gn, what can I say? I say that since Fn converges toward F in L2, since Gn converges toward F in L2, I have Hn that converges toward 0 in L2 of omega. Since D of Fn is convergence, since D of Gn is convergent, I have also that D of Hn is convergent in L2 of omega times 0 capital T by the difference and the fact that the derivative operator is a linear operator on the set of the random variable. But if I suppose that proposition 1 is true, what I obtain? I obtain that the limit of D of Hn is necessarily equal to 0. So that is limit of D of Hn is equal to 0 in L2 of omega times 0 capital T. And this implies that what is the limit of D of Hn? It is the difference between the limit of D of Fn and D of Gn. And so that the limit of D of Fn is equal to the limit of G of Gn in L2 of omega times 0 capital T. So this proposition, if it is true, ensure that the way I have decided to extend my operator, that is, say the following, okay, using approximating sequence, okay, suppose that F may be approximating by a sequence of S, okay, if the sequence of the related derivative is convergent, then I want to define the derivative as the limit of the derivatives in L2 of omega times 0 capital T. What I have done using the proposition 1 tell me that this way to define D of F is independent of the choice of an approximating sequence, because if I consider two of them, the limit of the related derivatives are equal, and so D of F is defined in an unambiguous way. It's exactly what I have proved here. Okay, the limit is the same for two different approximating sequences fulfilling the same kind of hypothesis, approximation of F in L2 with the sequence of the derivative that is convergent. Okay. So the idea of my extension this way is that natural, okay, that is extend the derivative operator, taking advantage of the fact that it is defined on elementary random variable, and taking advantage of the fact that the elementary random variable are dense in L2 of omega. Okay. So let's prove this proposition. To prove this proposition, I have to prove that C is equal to 0 in L2 of omega times 0 capital. And I say that, in fact, my conclusion is okay if I prove that for all, okay, H belongings to L2 of 0 capital T, okay, and for all F belongings to S, if I prove this, that the expectation of C H F is equal to 0. Here, the scalar product between being in L2 of 0 capital T. So I want to prove this. My first question is why C is equal to 0 if I fulfill this condition. But I fulfill this condition. If I fulfill this condition, what happens? I know that S is dense in L2 of omega. So if the expectation of this one with F is 0 for any F in S, okay, it means that this random variable, okay, is orthogonal to all the elements in S. By density, it will imply that they are orthogonal in L2 of omega to all the elements in the closure of S in L2 of omega, but S is dense in L2 of omega. So its closure is equal to all L2 of omega. So by density of C in L2, if I have this for any F, it implies that for all H belongings to L2 of 0 capital T, I have that C of H is equal to 0 in L2 of omega, that is in equal to 0 mu almost surely for any H, okay? And why I can conclude that C is equal to 0 here? In fact, keep in mind that if I consider if En is an orthonormal basis of L2 of 0 capital T, okay, and keep in mind that this Hilbert space is what we said, okay, separable, and so it exists a countable orthonormal basis for this Hilbert space, okay? So I can, using this orthonormal basis, I can write C as the sum over N of C En, I mean En. And from what I have put previously, these terms are equal to 0 mu almost surely. Here I have a sum that is countable, and you know that if you have, okay, all these one that are equal to 0 mu almost surely, okay, since, okay, I have only a countable number of such random variable, and with the fact that if you have the union of a countable family, a countable union of negligible sets, the probability of the union is also 0. You can deduce from the fact that all of them are equal to 0 mu almost surely, and from the fact that I have a sum that is a countable sum. If my sum here is not countable, I can't apply this argument, but here 0 mu almost surely with countability implies that this is equal to 0, okay, mu almost surely, okay? And so I have proved what I want. That is to say that in order to prove what I want to prove in this proposition, in order to prove my conclusion here, I have simply to prove this, that for any F in S and any H in L2 of 0 capital T, the expectation of this product is equal to 0. because by density argument, it means that all these scalar products are zero mu almost surely, and that since I can consider a countable basis for L2 of 0 capital T, I can decompose my stochastic process this way with all these terms that are zero because of my density, my previous density argument. Okay? So to do the proof of this proposition, I have simply to prove this. Okay? Let's do the job. So let's do the job. So I consider, okay, F belonging to S, H belongs to L0, L2 of 0 capital T. And I remind you that my job is to prove that I have this. F is equal to 0. Okay. So let's consider the term that interests me. And here I remind you that it's the scalar product in L2 of 0 capital T. What is C in my statement? C is the limit of D of Hn, but in the space L2 of omega times 0 capital T. So D of Hn converges toward C in L2 of omega times 0 capital T. And I said that since I have this expression here, I can write it as the limit when n goes to plus infinity of the expectation of D of Hn, H, F, scalar product in L2 of 0 capital T. And why I have this? Because I have this convergence in this space. I have the convergence in this space. Okay, so if you want, this is just a basic application of the Cauchy-Schwarz inequality, in fact, by Cauchy-Schwarz inequality, and from the fact that this one converges towards C, but in this space, L2 of the two variables, okay? So if you want to prove it at home, do the difference of these two, and then apply the Cauchy-Schwarz inequality to prove that the convergence of D of Hn towards C in L2 of omega times 0 capital T will imply the convergence of this term toward this one. It's just basic integration theory, okay? So I have this. But what is this term? I have proved the corollary previously. I have proved this corollary, what I have called this integration by part formula. This integration by part formula that we are going to use because I have what? I have the term I have in what I want to prove is this one, in fact, if you want, or this one, with here you have D of Hn, you have H, and you have here F belonging to S. So let's apply the corollary one. Let's apply the corollary one. If I apply the corollary one, I obtain for this one minus the expectation of Hn D of F H plus the expectation of Hn time F integral between 0 and capital T H of S dbs. So the limit of the term I am interested is just the limit of this one using here at the equality is equal because I have the corollary one. So let's consider, okay, the term that interests me now. So what can I say concerning this term? So I have this one, and I am interested in the limit. But what I know from the statement? I know from the statement that this one, Hn, goes to 0 in L2. This one goes to 0 in L2. This one is a random variable in L2. This one goes to 0. This product here is a random variable in L2 because I have something in S here. Okay, here it's a polynomial in Wiener integral, or mapping a function, or regular mapping Wiener integral multiplied by a Wiener integral. So I have here something in S. Okay, I have something in S here. Okay, and so by the Cauchy-Schwarz inequality, Cauchy-Schwarz implies that the limit of this term when n goes to plus infinity is equal to 0. Because Hn goes to 0 as stated in the proposition. At the end, what I have obtained that the expectation of CHF is equal to what? It's equal to the limit of this term. This term is equal to this one, and this one has a limit equal to 0. So this term is equal to 0. So I have proved that for any f and any f in S, any h in L2 of 0 capital T, this is equal to 0. And so from my previous slide, from what I have written here, C is equal to 0 in L2 of omega times 0 capital T, proving exactly the proposition 1. And so, since I have proved the proposition 1, as I have explained here, now I can extend the derivative operator using approximations argument with a definition of the derivative that will be unambiguous because it won't depend on the choice of the approximating sequence. And it's what we are going to see in this definition. Okay, so I denote by D, that will be the domain of my derivative operator now, the set of the random variable in L2, such that I can approximate then by a sequence in S. So this is always possible to do this, but I suppose that, so Fn converges toward F in L2, and I suppose that the sequence of the derivative is convergence. Okay, so it's a real hypothesis, this. Huh? I need to suppose this. It's not a consequence of the convergence of Fn toward F. If D of Fn is convergence, okay, then, okay, I said that F belongs to the domain D. So if I want to summarize what I have said here, D, that will be the domain of the derivative operator in the Malliavin sense, is the set of the F belongings to L2 of omega, such that there exists Fn in S with two things. Fn converges toward F in L2 of omega. So if I just put this condition here, okay, I have the whole L2 of omega because it's the density of F that give me this. But I add an extra condition that is D of Fn is convergent, convergent in L2 of omega times 0 capital T. And if I do this, I can define for F belongings to D, I define D of F as the limit of D of Fn that exists in L2 of omega times 0 capital T. And I have proved that using the previous proposition and the remark I have done related to this previous proposition, that here I have a definition that is not ambiguous. That is, this definition that doesn't depend on the choice of the approximating sequence Fn. because if I have two approximating sequences fulfilling, okay, they converge toward f and the associated derivative are convergent, then the limit of the derivatives are the same. Okay? So we have this definition for the derivative operator that will be, okay, the more general definition that we will have for the derivative operator in the Malliavin sense, okay, using approximating sequencing. So D is not the whole L2 of omega because, okay, I have to check that this condition here is fulfilled, that the limit of the derivatives, okay, exists in L2 of omega. So I can say several things concerning this. The first thing is that I can see that by construction, S, write it this way, is included in D. Of course, if you have an element that is in S, I can consider the sequence that is constant and I have all the things that are fulfilled, okay? So in particular, it implies that D is dense in L2 of omega, meaning that my derivative operator is not defined for all the random variables in L2 of omega, but it is defined on a set that is that big because it is dense in L2 of omega. Okay? It's the first remark that I can. Second remark. How D is in fact built. Okay? So I start from S and from sequences in S. I said that what I do, I consider sequences in S, okay? And I said that if the sequence is convergence and if the sequence of the derivative is convergence also, then the limit is in D, okay, by construction of D. So what is the way I build D? In fact, I consider all the sequences in S such that the sequence is convergent in L2 and the sequence of the derivative is convergent in L2 of omega times 0 capital T. And for these sequences, I said that the limit will be in, so in functional analysis or in classical analysis, the way I have built D is to build it from S and to consider, okay, the completion of S for this norm. What is this norm? A norm that takes into account the convergence in L2 of omega, it's this part here, and the convergence in L2 of omega times 0 capital T of the derivative. In other words, okay, what I have done in the construction of D is to say, okay, that I consider the Cauchy sequences in S that are the one fulfilling this, the Cauchy sequences in S fulfilling this one for this norm, because this one is convergent and this one is convergent, that is convergent for this part of the norm and convergent for this part of the norm. And since a priori I am not convergent, I add in the space the limit. That is this one. Okay, that is this one. And what is interesting with this argument is that I have two immediate consequences of this construction. So if I consider the set of all the Cauchy sequences and if I put inside all the limits, I obtain a space that is complete for this norm. Okay, so D is complete for this norm because by construction, okay, it is the completion of S for this norm. To make this statement clearer, think about the rational numbers and R. One way to build R is to say that, okay, I consider all the Cauchy sequences of rational numbers. I know that the set of the Cauchy sequences of rational numbers, okay, they may have limits that are not in the set of the rational number, but if I add to this set the limits of all the Cauchy sequences, what I obtain the whole R that is a complete space. It's exactly what I do here for this norm. I start with Cauchy sequences, okay, of element in S for this norm, and then I add to S the set of all the possible limits. This way, I build a set that will be complete as R is complete, okay? And it is built as the completion of S for this norm. As I repeat, Q, R is the completion of Q, the rational numbers for the classical distance, okay? So it's the first thing, okay? And what is more, okay? In fact, the set of the elementary random variable is dense in D for the norm D. Why? Also by construction, because if an element is in D, I know that there exists a sequence Fn such that Fn converges toward F, and such that by definition, D of F is the limit of D of Fn in the good space. So it means that, okay, using this norm here and using what I have here, I have Fn that converges toward F in the sense of this norm, implying that anytime I have an element in the domain, there exists a sequence in S by construction such that Fn converges toward F in the sense of this norm, implying that S is dense in D for this norm, as, if I come back to my example of the rational numbers and the real numbers, okay, as Q is dense in R by construction, okay? So I will define, okay, without ambiguity, the derivative operator for the elements that are in its domain D, D being defined on my slide here in red in definition 3, and I will consequence for element in D, D of F as the limit of D of Fn for any approximating sequence Fn, okay, in the previous sense, okay? And what will be nice in general is that we are going to prove some properties for the derivative operator extended this way. But in general, because S is dense in D for the norm D, okay, in order to prove this kind of result, what we will do, we will prove it for the element in S, and then we will extend by density argument to all D, okay, using the good norm. Okay, so it's exactly what we are going to do to study some properties of this derivative operator. So some properties that we are going to see now, okay, and some particular interesting, nice property of this extended version of the derivative operator, okay? So it's what we are going to do now, okay, and we are going to prove, oh, I am not sure that I will do all the proofs here, okay, so we are going to see several results now. And I think that I will do the proof maybe of the proposition 2, okay? And then, okay, I won't do the other proofs because they are a little bit technical, okay? But exactly in the same spirit, okay? But I just want to show you, okay, what will be the canonical principle of such proofs, okay, in this course. Proofs that we are going to do several times, but for the end of the session here, I will do it for the proposition 2. And then, okay, I will admit the other result, okay, just explaining what is the way to prove. So maybe I will do again a 5-minute break, okay, and I come back in a few minutes. Okay, so let's continue. So in fact, what we are going to prove now, okay, is that the derivative operator fulfills, what we call the classical chain rule. So in French, règle de dérivation des fonctions composées. Okay, so let just me remind what happened here. Okay, you know that if you have, okay, let's say F1, Fn that are C1 from R to R, let's say, or differentiable is enough. If you have, okay, phi that is differentiable or C1 from R to the power n into R, you can consider phi of F1 Fn, that is C1, okay, from R into R, and you have, we have what? You have that the derivative, the classical derivative is equal to what? It's the sum from I equal to 1 to n of d of phi over d of xi, f1 fn fi prime. Okay, so it's the classical chain rule formula, okay, that you use all the time, okay, in classical analysis with the classical notion of derivative. So here in the proposition 2, we have the analogous of this proposition. So here I suppose that I have random variables in the domain of the derivative operator. And here I suppose a mapping that is from R to the power n into R that is of class C1, but I add a little something here. I want it to be C1 and also Lipschitz, okay? Also Lipschitz. Remind you that what is Lipschitz in this situation? Lipschitz just means that, okay, if I consider phi of x minus phi of y, it is less than k time the norm of x minus 1, okay? And the norm you can take here is the norm you want because you are on R to the power n, where all the norms are equivalent, okay? So the norm you want here, the norm 2, the norm 1, the infinite norm, as you like, okay? Just keep in mind that C1 plus Lipschitz implies that the partial derivatives are bounded. Okay, it's easy to see this from this expression here, and the bounds, okay, may be found to be k here. Okay, if I have an optimal k, let's say. Okay, so if I have this, so if I have a random vector of element in the domain of the derivative operator, if I consider phi sufficiently regular, that is to be C1 and Lipschitz, then phi of f belongs to the domain of the derivative operator, and I have the classical formula that dt of phi of f is equal to the sum of the partial derivative of phi with respect to xi at f multiplied by the derivative in the Malliavin sense of fi, okay, at the point t. So it's the classical chain rule applied to my framework. I have two things to prove: that I have the stability of the domain by mappings that are C1 and Lipschitz, okay, and that I have this formula that is true. Okay, so let's duplicate the page. So I have this here. So I erase this part, what I have reminded here, and this. Okay, so first of all, I want to prove that phi of f belongs to D. Okay, so to prove that phi of f belongs to D, what I have to prove? One way to do is the following. I can find a sequence Gn in, okay, D such that Gn is convergent, so converge toward phi of f in L2 of omega, okay? D of Gn is convergent in L2 of omega times 0 capital T. If I find a sequence such that I have this, okay, but since D equipped with the norm D is complete, then necessarily I know that phi of f belongs to D and that D of phi of f is equal to the limit of D of Gn in L2 of omega times 0 capital T. Okay, why I have this? Because I have the completeness. Okay, it's the completeness that allow me to have this, the domain being complete. So here, the meaning of this one is that Gn is a Cauchy sequence in D, or is a Cauchy sequence, okay, for the norm D, okay? Since D is complete for this norm by construction, then, okay, the limit exists. That is necessarily this one. And what is more, okay, the fact that the limit exists implies that the derivative of the limit is equal to the derivative of the limit is equal to the limit of the derivatives. Okay, so in fact, here you have what you have to do in order to prove this result. Okay, and we have to find such a Gn and to compute at the end the limit of D of Gn in order to obtain D of phi of f. Okay, so it's what we are going, to do. So now let's start the proof. Let's start the proof. So it's the proof of proposition 2. Okay. And in order to simplify a little the notation, we are going to take n equal to 1. Okay, that is, I have F1 that belongs to D, okay, and I have phi from R into R, that is C1 and Lipschitz. Okay. So as I have previously said to you, okay, the way we are going to prove this result is doing 2 steps. And the several steps reasoning will be the key point on what we are going to do in the technical part of the course. Okay? So step 1, we are going to do the job for F1 belonging to S, the set of the elementary random variables. And in step 2, we are going to extend this result to the case of whole D using density arguments. So what happens if F1 belongs to S? Okay, well, it means that F1 is equal to F of, so it has this form here. as usual. Okay, so I have this. So if I consider phi f1, I can consider it as phi of f applied to by my Wiener integrals. Okay, but what can I say about phi of f? By composition, I have something that is of class C1, that is regular, class C1. And what is more, I know that f, okay, and its derivating, okay, as polynomial growths. And the same hold for phi, because, okay, keep in mind that phi is Lipschitz. So in particular, I can say that phi of x is less than k number of x plus, let's say, phi 0, for example. Okay, so you have a mapping. When it is Lipschitz, it is sublinear here. Okay. So I have here something that is regular, okay, and that has a polynomial growth because f has and phi also by its Lipschitz property. And so I can apply here the definition 2. And by definition 2, what can I say? That dt of phi of f is equal to what? It's just the sum from I equal to 1 to n of the partial derivative with respect to the i's variable of phi of f that I apply to the Wiener integrals multiplied by hi of t. But from classical analysis, I know what is this one. This one is just f prime, okay, of f multiplied by f prime. Or since it's a partial derivative here I don't have a prime, but I have d of f with respect to d of xi by the classical, okay, chain rule for mappings, okay? And so if I use this red argument in the green formula, I obtain what? The sum from I equal to 1 to n of what? Of phi prime of f of the Wiener integrals, these ones here that I have inside here, multiply by d of f over d of xi of the Wiener integrals also, hi of t. Here I have just simply f that I can remove from the sum because it doesn't depend on I. So I have f phi prime of f multiplied by what? By the sum I equal to 1 to n df over dxi at the Wiener integrals hi of t. And here, by definition 2, this is just dt of f simply. And so I obtain here phi prime of f dt of f, that is none other, I will suppress this one, yeah, that is none other than what I want to prove here for n equal to 1. When n equal to 1 here, okay, you have just phi prime f multiplied by dt of f. Okay, so I have done the job when f1 belongs to S. Okay, so it's the step 1 that is okay. Step 2, let's suppose that f1 belongs now to D, not to S. Okay, so meaning that I can't apply the definition 2 in this situation because I don't have it. But I know that then D, oh, excuse me, we know that S is dense in D for the norm D. And what is the meaning of this one? There exists a sequence, so Fn, okay, such that, so let's call it, so yes, just give it a name this way, because I don't want, I have F1 here. If I write Fn, I can do confusions here. So I will just suppress this one and I put F1n here. Okay, it's an approximating sequence for F1. So there exists F1n such that F1n converges toward F1 in L2 of omega. Okay, it's such that, okay, D of F1n converges toward D of F1 in L2 of omega times 0 capital. Okay, so I have this. And now I am interested in phi of F1. Okay. So I have this. So what can I say? First, I can say that phi of F1n converges toward phi of F1 in L2 of omega. So why I have this? Be careful, the convergence in L2 is not stable in general by continuous mapping. But here, keep in mind that my phi is Lipschitz. My phi is Lipschitz, and so from the convergence of F1n toward F in L2, since I have the Lipschitz property, okay, I can deduce the convergence of phi of F1n toward phi of F1 in L2 just using this inequality. So because this. Okay. So be careful here. There exists a sequence. So S is dense in D. So there exists a sequence in S such that I have this. Okay. So I have this one. What is more? From step 1, F1 of n is in S. So from step 1, I have D of phi F1 n, that is equal to what? That is equal to F prime F1n D of F1n, because F1n belongs to S. And so from step 1, I can use my previous result. Okay? Okay, so I have this. So if you have understood what I have said just before, okay, what I have done, this one here. So this is my study plan here. I want to find, okay, a G in D that converges toward phi of F and such that D of Gn is convergent. And in this way, if I do the job, okay, I have my result where the limit I am interested in will be D of phi of F. So if I am here, my Gn will be this one, in fact. My sequence, my approximating sequence will be naturally phi of the approximating sequence of F1. Okay, so in fact, in order to conclude, I have to study the convergence of this one. I have to study the convergence of this one. So what can I say concerning this? If I am interested in D of phi of F1n minus D of phi so just have a look on what I do here. Okay. So, excuse me, to be clear. I can write the following thing. To conclude, it remains to prove that D of phi of F1n converges toward phi prime F1 D of F1 in L2 probe. So I do it. To conclude, it remains to prove that I have this, because according to what I have said, okay, here I have a sequence, okay, phi, this one is a sequence in D that approximate phi of F1. The related, if I prove that the related derivative are convergent, I know that the limit is in the domain, okay, because the domain is complete and so closed, okay, and that the derivative of the limit is equal to the limit of the derivative. So if I prove this, I will prove that this sequence is a sequence that is convergent with a limit that is this one. So to conclude, it will prove that this one, because in this case, since the domain equipped with the norm D is complete, because in this case, using the completeness argument, I have phi of F1 that belongs to D and D of phi of F1 is equal to the limit of the phi F1n. That will be, in this case, if I prove this, phi prime F1 D of F1. That is what I want to prove. Okay, so the only thing it remains to prove is that I have this. Okay, I have to prove this. So let's prove this. So let's consider that D of phi F1n minus the limit I am interested in. I know that this one has an expression that is this one from step one. So I can write phi prime F1n D F1n minus F prime F1 D of F1. And keep in mind that I have some hypothesis. I know that F1n converges toward F1 in L2. D of F1 converges toward D of F1 in L2. So, okay, can say something. So let's do the following. I will express, because here you have n and n here in both sides, okay, so we are going to introduce intermediate terms, okay, in order to study only the convergence, okay, from one of the two parts of the product. So I can write the things this way. I write them as phi prime F1n minus phi prime of F1 multiplied by D F1n. And if I do this, okay, I obtain what? I obtain, I can write it this way, plus phi prime of F1 D F1n. So it means that I add this term and subtract the same, okay, in order to preserve the equality here, minus D of F1. Okay, and my job is to prove that this term goes to 0 in L2 of omega times 0 capital T. So let's examine all the terms. So what I know. So this one, I know that it is bounded, because phi is Lipschitz, so its derivative is bounded. What I know for this term I know that I have this. So this term goes to 0 in L2 of omega times 0 capital T. So it's nice because this product, so I have something that is bounded here, something that converges towards 0 in L2 of omega times 0 capital T. So no problem. All this part here converges towards 0 in L2 of omega times 0 capital T. So it's exactly what I want to have. Okay. Okay. For this one, it's slightly more complicated, because what can I say about this one? D of F1 of n is something that is convergent in L2 of omega times 0 capital T. So I have something here. Let's change the color. So I have something here that is convergent. And so bounded in L2 of omega times 0 capital T. Okay, convergence, so bounded. So it remains to check what happened for this one. I know that F1n converges toward F1 in L2. But a priori, okay, if I have the convergence in L2, okay, it implies nothing concerning what happened if I compound by a mapping that is continuous. Phi prime is continuous, okay, but if you have un that converges toward u in L2, in general, f of un doesn't converge toward f of u, even if f is continuous. So I have a little problem here to conclude, but in fact I have not. So be careful on the argument I will use here. Okay, I will use the green things here, because what is nice, a way to converge that is preserved by continuous mapping is the convergence almost sure. If un converges toward u almost surely and f is continuous, I know that f of un converges toward f of u almost surely. But here, unfortunately, I don't have the convergence almost sure. But I have the convergence in L2. In fact, I can do what I want here, because what is my aim? My aim is to find, as I have explained to you, a Jn, okay, that converges toward phi of F1 and such that D of Gn is convergent. I need to find one, okay? A natural candidate was phi of F1n. But if I do this using the density argument, I have only this. But what I know that F1n converges toward F1 in L2. I know that there are some links between convergence in L2 and convergence almost sure. I know that convergence almost sure plus domination implies convergence in L2, and I know that convergence in L2 doesn't imply in general the convergence almost sure, but I have the convergence almost sure for a subsequence. I have the convergence almost sure for a subsequence. And so here, I can directly start to work with this subsequence. The subsequence won't change the convergence for these two things here, but I can use here and almost surely doing an extraction. And if I do this, it's finished because it's closed my problem. Why? Because if I suppose that I have the convergence in L2 and almost sure, something that I am supposed to be able to do because I just have to consider a subsequence. Now I have F1n that converges toward F1 almost surely. And so phi prime being continuous, I have this one that converges toward 0 almost surely. But phi prime is bounded because phi is Lipschitz, being bounded. And so I have what I want. Because this term is bounded in L2 of omega times 0 capital T, this one is convergent. So I have my term here by convergence towards 0 almost surely being bounded, okay? I have that this one converges towards 0 in L2 of omega. If I multiply something that converges towards 0 in L2 of omega by something that is bounded in L2 of omega times 0 capital T, I will obtain a product here that is convergent towards 0 in L2 of omega times 0 capital T. In fact. Okay, so to summarize, this term converges towards 0 in L2 of omega times 0 capital T. By my argument, this term converges towards 0 in L2 of omega times 0 capital T. Okay, using this little extraction trick. And so at the end, okay, this one implies that this one goes to 0 in L2 of omega times 0 capital T. What I have done exactly what I want. I have found a sequence converging toward phi of F1 such that the derivative of this sequence in D converges toward this one. From the fact that the domain is complete, I know that the limit of my sequence is in the domain of the derivative operator, and that if I want to compute the derivative of this one, it's just the limit of this derivative, the limit of this derivative that is equal exactly to this one. And at the end, what I have at the end, okay, I have that the derivative of this term is equal to this one. Derivative of this term that is equal to this one. That is exactly what I want to prove here for n equal to 1. Okay? So for n equal to 1, I have done the proof of the proposition 2, doing it in 2 steps. First, for elements that are in the set of elementary random variable, where in fact I just have to use the classical chain rule and the definition 2. And then, okay, using an approximation argument to extend from step 1 to step 2, the step 2 being the step where F1 belongs to D. If F1 belongs to D, okay, I can consider an approximating sequence in D of function in S, because S is dense in D for the norm D, okay? And just my little trick in order to be able to compute and to conclude at the end is state, okay, I have just the convergence in L2 here, but I can add here also the convergence in Mosher, because I just have to consider an abstraction, and so I can consider that I have also the convergence almost sure without loss of generality here. And then, okay, I see that using this, phi of f1 of n, that is a natural approximation of phi of f1 because f1 of n is a natural approximation of f1. I see that I have the convergence in L2 of this one. I have the convergence of this term in L2 of omega times 0 capital T toward this limit. And so at the end, this one belongs to the domain. And the limit, so the derivative of this one is just the limit of this derivative that is equal to this one. So the derivative of this one is this one. That is, I repeat, exactly the formula I want to prove, okay, previously. Okay, so I have the proposition 2, okay, and here what is interesting, so the result is interesting for sure, and what is also interesting is the way I prove, using a two-step argument, do the proof for elementary random variable, and then extend using the fact that my operator has a domain that is closed for the norm, okay? I have this one. So it is possible to extend in some sense this proposition in the following way to obtain the proposition 3. The proposition 3 will tell you that if you have element in the domain D, and if you consider a mapping that is only Lipschitz, so no more C1, then phi of D belongs to the domain. Okay, so in some sense, the proposition 3 tells us that the domain is stable by Lipschitz mapping. Okay, and of course, it's not possible for me to have the formula because if phi is not differentiable, I can't consider the partial derivative. But I have the stability of the domain. So if I want to do the proof, I won't do it here, okay? But if I want to do it, two steps. First, suppose that phi is C1 and Lipschitz. And the result is just an application of the proposition 2. Okay. Step 2, suppose that phi is only Lipschitz. If phi is only Lipschitz, I can approximate it using classical argument of classical analysis by mappings that are C1 and Lipschitz. And then I pass to the limit using the same kind of argument as the one I have used previously. Why this proposition 3 is very important in our framework, even if I don't do the proof. Keep in mind where in the course of stochastic calculus, you have used Lipschitz mapping. In fact, you have used Lipschitz mapping in the theorem that ensure the existence and the unicity of a solution of a stochastic differential equation. The conditions in order to have the existence and the unicity of a solution to a stochastic differential equations are the Cauchy-Lipschitz condition, and these Cauchy-Lipschitz conditions implies that the coefficients have to be Lipschitz in the second variable. Okay, this regularity, that is the one that ensures the existence and the unicity of a solution, will be the one using the proposition 3 that will allow us to have the fact that if I consider a stochastic differential equation, okay, x capital T, considered as a random variable, will always be in the domain of the derivative operator. I will have in my domain D all the solutions at particular times of all the stochastic differential equations fulfilling the Cauchy-Lipschitz condition. And for the application, it's something that is important because it means that the derivative operator will be well defined for solutions of stochastic differential equations, okay? So solution of stochastic differential equations that are the one that I use in order to model, okay, the dynamic of risky asset in mathematical finance. So this proposition 3, that is a consequence of the fact that the domain equipped with the norm is something that is complete and so closed, okay, is fundamental for the application in mathematical finance. in the domain, I have enough random variable. The domain of the derivative is not whole L2 of omega, but I have sufficiently random variable inside, okay, in order to be applied to mathematical finance framework. Okay, so let's conclude quickly with two last results. So this one, that tell you the following. If I have a random variable in the domain of the derivative of operator, then if you consider the conditional expectation of f given fs, I have something that is still in the domain of the derivative operator. So if you do conditioning, you are still in the domain of the derivative operator. And what is more, you have a nice formula that tell you that the derivative of the conditional expectation is the conditional expectation of the derivative up to a little term that is this indicator function here that you don't have to forget inside. Okay? So once again, I won't do the proof of this proposition, but if I want to do the proof, what can I do? I can do the proof for f belonging to S. And in this way, I can do everything using the definition 2, in fact. And then in the step 2, I extend it for f in D using the density of S in D for the norm D. Okay? So it's a little bit long to do it, but not difficult. It's exactly the same kind of proof as the one I have done in the proof of proposition 2. I have a nice corollary for this proposition. This corollary tells me that if f is in D and fs measurable, dt of f is equal to 0 when t is strictly greater than s. In fact, I have already seen this kind of result. Let's come back to what I have done at the beginning. So not here, the very beginning. Here. In the definition 2, that is the definition of the derivative in the Malliavin sense, okay, for elementary random variable, I have my remark C in the remark 2 that tell me that if I have an elementary random variable, we have done the proof that if I am fs measurable, dt of f is equal to 0 if t is strictly greater than s. The proposition, or this corollary, that is a consequence of the proposition 4, so the corollary I am interested in here, tell me that it is true not only for elementary random variable, but for all the random variable in the domain of the derivative operator. I have dt of f that is equal to 0 for t strictly greater than s for f in D, not only for f in S. Okay? So why this corollary is very easy to prove from the proposition 4, but from the fact that if f is fs measurable, but the conditional expectation of f given fs is equal to f. So by proposition 4, I have that dt of the conditional expectation, that is in this case only dt of f, is equal to this expression here, that is indicator function of t less than s conditional expectation of dt of f given fs. And this one, 0 if t strictly greater than s, because I have the indicator function here. Okay, so this proposition 4 allow me to have very simply the corollary 2 that extend the third point we have seen together at the beginning of the session in the remarks 2 after the definition 2. dt of f is equal to 0 when t is strictly greater than f, when f is an element of the domain that is fs measurable. Okay, so I have this one. Finally, I will conclude with the product rule principle. What we have seen together? We have seen together, and we have done the proof, that if we have f and g that are elementary random variable, then the product is an elementary random variable. And if I want to compute thanks to definition 2, the derivative of the product. The derivative of the product is simply the formula we have classically in mind, that is uv prime is equal to u prime v plus uv prime. That is exactly what I have here. Okay? And this is easily obtained here from definition 2. A natural question is it possible to extend this formula in the case where f and g are only in the domain D? So that is, okay, this proposition is to extend star for f and g in D. So suppose that you have it. So suppose that you have this nice formula. So let's have a look on the integrability condition we have for the stochastic processes and the random variable. So if f and j are in D, I know that here I have something in L2 of omega. Here I have something in L2 of omega times 0 capital T. Here I have something in L2 of omega. Here I have something in L2 of omega times 0 capital T. If I want this formula to be true, I know that this one has to belong to L2 of omega times 0 capital T. But if I write this way, I have a problem. Because in general, when you multiply something in L2 of omega by something that is in L2 of omega times 0 capital T, you don't obtain something that is in L2 of omega times 0 capital T, you obtain simply something that is in L1. The same all for this one. So it means that a priori, and just having a look on the integrability condition, such a formula a priori is not possible in great generality. Here we have it. We have it because we only work with elementary random variable, a set that is stable by product, and keep in mind that for S, the elementary random variables are random variables that have moments of all orders because they are regular mappings of linear integrals where the mapping has a polynomial growth. Here it's no more the case if I replace S by D. Okay. And so it means that it's as usual, okay, if I have L2 times L2, in general, I am only in L1 and not in L2. And if I want a product to be in L2, I have to make the integrability conditions more flexible. So in fact, what I want you to keep in mind is the following. This formula will be true when it will have a sense. That is, when this product will be in L2 and when this product will be in L2. In order to do this, if I want to state a general result, I can add, okay, integrability condition to make it okay. A first condition, that is this one that I can do, is the following. If I suppose that I am in the domain for both of them, and if they are essentially bounded, I have no more problem. Because, okay, when I multiply things that are in L2 by something that is essentially bounded, so here it will mean that this one is in L infinity, this one in L infinity. So if you do the product of something in L infinity by something in L2, you will be in L2. No problem with this, okay? So if I suppose this integrability condition, now in terms of integrability, this formula has a sense, and in fact, we can prove that it is true. It's the same here, okay? I can do this hypothesis that if I suppose that they are both in D, F is in L infinity, and D of F, okay? So the square of the norm of D of F in L2 is in L infinity. If I do this, from the fact that F is in L infinity This one is in L2 of omega times 0 capital T. And from the fact that this one is in L infinity of omega, this one is in N2 of omega times 0 capital T. So you have here an integrability condition on F and on its derivative in the Malliavin sense, allowing to give sense to good integrability condition here. And so it's possible to prove that this proposition is true. And what is more, okay, so it was to show you why intuitively I need to improve integrability condition to expect to have this formula in grid generality for elements that are in D and no more in S, okay? And if I want to prove them explicitly, the idea is to use as a first step this one, okay? And using my integrability condition to prove that you can pass from step 1 to step 2, passing to the limit. And the fact that I can pass to the limit without problem is because I have this integrability condition. And in some sense, you will have a reasoning that will make use of kind of dominated convergence theorem. Okay. Okay, so it closes what I want to say today concerning the Malliavin derivative. So to summarize, elementary random variable definition, okay, of the derivative in the Malliavin sense for this elementary random variable. I have proved that it has a link with directional derivative in the sense of the Cameron-Martin space, okay, in order to show you that this derivative is not coming from nowhere. Then we have studied some property of the derivative operator for element in S. We have studied the product rule principle, for example, and other nice properties that are first step toward integration by part formula. We have used this integration by part formula to be able to extend, using approximating sequences, the derivative operator from S to its more general domain that I have called calligraphic D. And on this domain, we have seen that the derivative operator fulfills several properties. It fulfills the chain rule for mappings that are C1 and Lipschitz. The domain is stable by Lipschitz mapping, and that I have the product rule principle if I enlarge a little the integrability condition on F and J. Okay, so I know that this session is a session that is, let's say, piece of mathematics. Okay, so I want you deeply to understand the definition and the propositions we have seen together, and try to be familiar with the several steps argument, using density argument to pass from one step to the other, that I will use, okay, also next week in the next chapter, that will be to study an operator that is in relation with the Malliavin derivative. This operator is called the score integral. The score integral, that is an integral that will extend the Ito integral you have defined in the first semester, and an operator that is, okay, that has a nice relation with the Malliavin derivative, that is the adjoint operator. Okay, so see you next week for the next session. Bye-bye.